Hi, this is Mr. Mack again. We had a little trouble the other day, and people kept coming in, so I know I said I was going to go back on that other video, but it just turned out that um, things happened, and so I ended that video. We'll call that the probability and stat video session 1 part A, and this is probability and stat video part B. Now what we've come to now is the next topic, which is subsets. Now, it's a pretty simple concept. If you have two sets, a set A and a set B, then set B is considered to be a subset of A if every element that is in set B is in set A. Now, start off with this picture here, this Venn diagram. Now notice the universal set is the rectangle here, and we have a set A represented by this oval here, and a set B represented by this oval here. Now the relationship B is a subset of A is illustrated by this Venn diagram, because notice if anything is inside circle B, then it's automatically inside circle A, because circle B is entirely contained in the interior of circle A. And we would write that in this way: B is a subset of A. Now, the symbol for subset, notice it's rounded, and it looks a lot like, oops, I'm just trying to, not being able to, there we go. It looks an awful lot like a less than or equal to symbol, but it's not pointed, it's rounded. But the fact is that, and let me erase this. This is, I don't know how that got there. Okay, so in other words, what we're saying is that B is a set that's smaller than or equal to A, in that it has only elements of A, and there might be elements that are in A that are not in B. Notice those elements would be in, say, this region right here, but everything that's inside B is inside A. Now, a concrete example. Let's say we have the set 1, 2, 3, 4, 5, 6, 7, and then we have a container for another set here, B. If there's nothing in B, of course, then everything that is in B is in A, because we don't have anything. But imagine we have an element from set A in set B, say 6, for example. B would be the set 6, and it is a subset of set A because everything that's in B is in A. We could have other elements in here also. So if 3, 5, 6, and 7 are in B, they're all in A, so B would be a subset of A. Now, the one question you might be asking yourself is, what if let's get the whole 4 here, there we go. What if every element that's in A is also in B? I'm missing a 2, there we go. Now, notice in this particular case, A and B are the same. We would still say that B is a subset of A. There is a distinction when you have a set B that's a subset of A and there's something that's in A that's not in B. We would say B is a proper subset. But in this case right now, B is just a subset of A. Now, if you look at the examples here, we've got an example where A is the set 1, 2, 3, 4, 5, 6, 7, 8, and then B is the set 2, 4, 6, 8. Now it says, is A subset of B? Well, that's not true, because there are elements in A, 1 for example, that are not in B. For A to be a subset of B, it has to be less than or equal to B. And in this particular case, A has things that B doesn't have, so A is not a subset of B. Let's just write a no here. Now, in this case, is B a subset of A? Well, yes, 2 is in A, 4 is in A, and 6 is in A, and 8 is in A. So everything that's in B is in A, so yes, B is a subset of A. Now, a couple more concepts here. Set operations. We have complements of sets, we have union of sets, and we have intersection of sets. I don't think that, well, we've got another page, but we'll start with complement. Now, the complement of a set is everything that is in the universal set that is not in the given set. For example, let's go back up here to our example where we have the set A, and maybe we could get rid of a couple of values from set B. Let's imagine that set B is the set 3 and 6. Maybe we should move these around so it's easier to remember. And then A is going to be the set 1, 2, 3, 4, 5, 6, 7. Now, the complement of set A, and a lot of times we use this symbol, the complement of set A, oh, no, I'm sorry. Let's actually use, what's happening here? There we go. Let's this is not working well here at the moment. Let's go down here and find some space where we can work. All right. Imagine we have the universal set U, and let's let be 1, 2, and we'll have a set A, 3, 4, 5, 6, 7, 8. Okay, so as you can see, the universal set is the set 1, 2, 3, 4, 5, 6, 7, and 8. And A is the set 3, 4, 6. Now, the complement of A, and we do that like this, although sometimes they'll use a little accent mark up in the exponent point on the A. Anyway, the complement of set A is going to be the elements that are in the universal set that are not in the set A. So that would be 1, 2, 5, 5, 7, and 8. Now notice, it's always true that A union A complement is equal to the universal set. So if we take the complement of a set, we get everything that is in the universal set that's not in A. A lot of times we read that as not A. Okay. And there are a couple of examples for you to kind of go through. Now, let's take a look at the next page. Now, the union of two sets. Now, notice the symbol. I need another pointer here. Notice that the union symbol is a U, and the other set operation is intersection. And notice intersection is the symbol that looks like the union symbol, but it's not a union, it's upside down. So we think of that as the intersection. Now, if we were to look at this Venn diagram right here, and we were to put, if we were to color in the union of A and B, that would be everything that's in A and everything that's in B. So if an element was in either set, it would be in the union. Let's take a look at a simple example. A being the set 1, 2, 3, and B being the set 3, 4, 5. A union B A union B would be the set 1, 2, 3, 4, 5. Now notice 3 is in both sets, but we don't list it twice in the set of the union because actually elements are either in a set or they aren't in a set. So to list 3 twice would still just be saying that 3 is in the set. It doesn't make it any different from 3 being listed once, which means that 3 is in the set. So the union of the set A and B is kind of like a set where we just, all the elements that we find in both A and B, in either A or B or both, get to be in the union. Now, if we were to shade the intersection here, if this were a Venn diagram and we were to shade the intersection, we would just shade the overlap of the 2 circles. And let's use this same illustration. If A is the set 1, 2, 3 and B is the set 3, 4, 5, then A intersect B would be the set of elements that are found in both sets, and in this case that would just be the element 3. So if you look up here, it says the intersection of 2 sets is the set of elements that they have in blank and is denoted by the symbol intersect. So that it's the intersection of 2 sets is the set of elements that they have in, pause here, or give me a word. The word is in common and is denoted by the intersection symbol. The union of 2 sets is the combination of all elements in, well, is the combination of all elements in both sets, and is each element only being listed once, and is denoted by the U symbol. We read set A or set B or set A and B. All right. Here are some examples for you to try. Let's maybe you'd want to pause for a moment and work through these because what I'm going to do now is I'm going to well, actually, there's not a whole lot to do because the answers are given. So you might want to just take a look at these. The set of A is the letters in the word mathematics, and the set B is the set A, B, C, D, E. So we've got an M, we've got an A, we've got a T, we've got an H, we have an E, we have M, that's already there. We have another A, we have another T, we have an I, and we have a C, and we have an S. And then to that, we'd add A, B, C, D, and E. So notice then, when we add the B and the D, we have the set A, B, C, D, E, H, I, M, S, and T, which is the union of the letters A, B, C, D, and E, and the letters in the word mathematics. Number 2, the universal set is the set of integers less than or equal to 16. A is the set of multiples of 4 that are less than or equal to 16, and B is the set of all factors of 16. Oh, okay. Construct a Venn diagram to represent this information. Well, I'm a little nonplussed here because with integers less than or equal to 16, that includes 0 and -1 and -2, and it keeps on going forever in that direction. So how about if we change this for the moment to positive integers? Well, actually, we don't need to cross out integers. We'll just put a little caret in here and say positive integers. So in other words, if we were to list the set U, it would be the set 1, 2, 3, ... up to 16. And A is the set of multiples of 4 that are less than or equal to 16, which would be 4, 8, 12, and 16. And B would be the set of all factors of 16, which would be 1, 2, 4, 8, and 16. Now, the Venn diagram, okay, so we have the Venn diagram U. Here's the set A, here's the set B. Now, 1 would go in B, but not A. 2 would go in B, but not A. 3 would go in U, but not A or B. 4 would go in A and B. 5 would go in U, but neither A nor B. 6 would go in neither. 7, neither. 8 would go in both A and B. 9 would go in neither. 10 would go in neither. 11 would go in neither. 12 would go in A, but not B. 13 would go in just U. 14 would go in just U. And 15 would go in just U. And then 16 would actually go in both of them. It's a little difficult to see, but we've got 4, 8, and 16 in this intersection here. So A intersect B would be the set 4, 8, 16. And A union B would be the set 1, 2, 4, 8, 12, and 16. All right. Oh, the number, okay. C, the number of elements in A intersect B would be 3. What we're doing here is we're counting how many elements are there. And not A would be, let's see if I can get this in here, 1, 2, 3, 5, 6, 7, 9, 10, 11, 13, 14, and 15. Or the complement of A. So, there you go. Example number 3, we've got 540 seniors at PHUHS. 335 of them like hamburgers, 287 of them like hot dogs, 220 like both. Construct a Venn diagram to represent the information. How many students don't like either hamburgers or hot dogs? Okay, so let's just put this universal set up here. The universal set this time is the 540 PHUHS students, studs. And we've got those that like hamburgers, we'll call that the set H, and well, maybe the set HA, and the students that like hot dogs, we'll call that HO. Now, to build this, actually this time we're going to actually just be counting how many students are in each of these sets. Since there's 220 that like both, that's 220 goes in here. Now, if you look at this, there's a total of 335 students that like hamburgers. So if we have 220 in here, then we need another 115 that like just hamburgers and not hot dogs, because then the number of students inside the HA circle is 115 plus 220, which is 335. Now, the number of students that like just hot dogs, well, the total number of students that like hot dogs is 287. And since we know 220 of them like hot dogs as well as hamburgers, there will be 67 students that only like hot dogs. Now, the other question is what goes in this rectangular part right here? Well, there's a total of 540 students, and if we subtract the sum of 115, 220, and 67 from those, we will get the number of students that like neither. Now I'm looking here and I don't see a calculator, so please bear with me for a moment while I pull up the calculator. And I'm back. So now we have 540 minus, in parentheses, 115 plus 220 plus 67, and we get 138. So there would be 138 students down in this particular section right here. Now, we can answer questions about our example from this Venn diagram. Of course, we need the Venn diagram in the window. Okay, it says how many students don't like either hamburgers or hot dogs? Well, obviously that's 138. How many students are in the not hamburger? Well, there's a total, I've forgotten, but it was up here in the problem. Oh, here it is. There's a total of 335 students that like hamburger. So 540, all the students, minus the ones that do like hamburger, will be the number that don't like hamburger. And what is that, 205? I think it's 205, yes. 205. So there's 205 students that don't like hamburgers. Okay. Now, example number 4. In a survey, 113 business executives were asked if they regularly read the Wall Street Journal, Business Week, and Tampa Bay Times. The results of the survey are, and you see all of that, construct a Venn diagram. Well, now the Venn diagram's already constructed for us, but we're going to have to do what? The Wall Street Journal, WSJ, the Business Week, BW, and TBT, Tampa Bay Times. Now, the easiest way to start this would be to start with the 42 that read all three. It would go in the place where all three of the circles overlap. Now, it says 67 read the Journal and the Times. Now, let me just put a little arrow up here. The Journal and the Times is this overlap right here. So inside this total overlap between the Journal and the Times, we want 67. We already have 42, so right here, we would put, what would we put? 25. Now it says 55 read Business and Times. So Business and Times is 55. Now, this is Business and Times. You already have 42, so the number that would go in here would be 55 minus 42, or 13. Now, Journal and Business, that's this overlap right here. It's 56. We already have 42, so 14 would go right here. Now, it gets a little more complicated. Now it says 88 read the Times. So there's a total of 88 business executives that read the Times. Now what we have to do is we have to see how many are already inside our circle. Now, we have 42 and 13, that's 55, plus 25 is going to be 80. So 55 plus 25 is 80, and there's a total of 88, which leaves 8 for this part right here. So if we were to ask a little bit later, how many of these executives read only the Tampa Bay Times, the answer would be this 8 right here. All right, now we know that 74 read the Business Weekly, so there's 74 inside this circle. Now, we already have 55 plus 14, that's 69 in this circle, and since we're looking for 74, that's 5 more. So there would be 5 business executives that only read Business Weekly. And then, well, not finally, but next, there were 87 that read the Wall Street Journal. Now, this is 67 right here, plus 14 is 81, and since 87 read the journal, there would be 6 more here. Now, it's possible that if we add all of these numbers up, we won't get 113. Whatever there is shy of 113 would be what would go inside the rectangle, but outside the 3 circles. So what we have to do now is we have to add, well, you know, we can save ourselves a little time, because if I know that this plus this plus this plus this already is 87, so I can just say 87 and then plus 5 plus 13 plus 8. Now that gives me 1826 plus 87 is a 3, and 2 plus 8 is 10, plus the carry is 113. So there aren't any that don't read at least one of the 3 journals. Okay, now how many read the Times, the Tampa Bay Times, or the Business Weekly? Now, or means one or the other or both. So what we would do is we would add all of these numbers together. It might be easier to just note that if you added all of these numbers together, there would only be one more number to add, because this is 0, to get 113. So if we subtract 6 from 113, we would get 107 actually read the Times or the Business or both. Now, how many don't read the Wall Street Journal? That one's probably easier to do by adding up the numbers that aren't inside the WSJ. That would be 18 plus 8, or 26. Now, if you look at E, that's not the Tampa Bay Times intersected with the Business Weekly. Okay, now that means, oops, I'm trying to get this arrow here. There we go. That means we want to be outside this circle and intersected with inside this circle. So outside this circle, intersected with inside this circle, is just these 2, which is 19. Now, how many are in the union of J and not B? Okay, so we're putting everything that's inside here along with everything that's outside here. So that would be the Wall Street Journal, which we know is 87, plus 8, and actually plus 0. So 87 plus 8 would be 95. Okay, now that is an intersection to the concepts of set theory that you're going to need. I'm going to stop this video and then start a third one for the probability.